And then I started recording, so yeah. And then share screen. Can you see the paper?
Yes.
Okay, great. So this paper is about, as the paper, I like papers like this where they're not using some kind of weird acronym that they've made up to describe the method. So this is about temporally consistent survival analysis. And so the paper is bringing together two separate concepts. One of them is survival analysis, which probably comes out of trying to perform statistical analysis on the effects of treatment on patients in the medical industry, or just maybe trying to figure out the impact of a disease on a person. And the idea is that you're trying to figure out how long the patient will survive. That's why it's called survival analysis. It's like, how far into the future will they survive? And temporally or temporal consistency is an idea from reinforcement learning, dynamic programming, where the idea is that the way it's described in reinforcement learning is that the value of your current state should be equal to like the expected value of all the states that you could transition to from your current state. And we'll go into that a little bit more because I'm not describing it that well, but I wanted to give like a key idea. Oh, in case someone else. Yeah, okay. I wanted to give a key idea behind why temporal consistency and dynamic programming is so powerful, or why you see it in reinforcement learning and other parts, is because there's a lot of problems when they're described. They might be something like find the way to arrange these objects such that they cover the smallest amount of area, or something along those lines. And there's like a factorial number of ways to organize a set of objects. With dynamic programming, instead of having to look at all of the factorial different number of ways of doing something, you only have to look at like, for example, if it's going to take you k actions or k steps to organize your objects, and you have n objects, it would take you k times n steps. So it goes from solving a problem taking like factorial time to taking like squared amount of time, or some polynomial amount of time. So that's or just squared. So that's the main reason. It just like really reduces the amount of solutions that you have to look into by making it a step-by-step process. And that's why it's so powerful as a method, because it allows you, the main thing is it allows you to be more data efficient by enforcing like the assumptions of dynamic programming, which are the main assumption being Markov assumption. So let's get into it. I'll start off with the two, just by naming again the two applications of survival analysis that they mention here. One of them is that it's used for modeling patient outcomes in clinical studies. And another one, which is probably the one, since the two authors are working at Spotify, that they are using it for, is predicting customer retention in subscription-based businesses like Spotify. And there's a key additional element to the problem that they're trying to exploit, which is that usually in survival analysis, you get a description of the patient or the customer at a single point in time, and then you're given a label of how long they survived or how long they stayed with the company in terms of their subscription. But more and more frequently now, you're going to get multiple data points about the same person, and those data points could change based on, it could be as simple as just knowing the time. For example, if a person signed up in 2020 and they stayed exactly the same for 5 years, there would be a difference in the number of years they had been with the company, and that would be a feature that you could use. But there could be a number of other ones, like for example, in a patient who's being offered a treatment for cancer, maybe their weight would be an indication of health. So maybe if they had lost like 30 pounds during the treatment, maybe they would be less robust or like less likely to survive, just because it's not they're too skinny for their height. They don't have something along those lines. That's kind of made up, but so you start seeing this as a dynamic problem because the customer or the patient, the person, is changing over time, and you have measurements of that change. And so the question that they're trying to answer here is, how can we exploit this additional information to come up with better survival distributions at any given point in time for any given candidate? So they say to here, can we take advantage of sequential data to improve survival predictions? And the way that they want to take advantage of the sequential information is through temporal consistency, the temporal consistency condition. And so the main assumption that they make in their problem formulation for this problem, and I hope the problem is clear now that I've described it, is that they assume that sequences of states follow a Markov chain, which means that you only need to know the current state to infer what the next state is going to be. And so that's like the major assumption that they make. And because they make that assumption, they actually can they can actually enforce temporal consistency because it falls out of making that assumption. Okay. Let's see, is there anything else that I want to say? No. Maybe just that. So like we said, this is a survival analysis, and I don't know how familiar everyone is with reinforcement learning or dynamic programming, but you always have some state space, which is the description of, in this case, it would be the description of the person in survival analysis. Although survival analysis doesn't only have to be applied to people, it can be applied to other problems, but let's stick to that as our like example when we're talking about this. Like it would be your description of the person, and there's a special terminal state which they include as well, which is the when the person has passed away or left the company. So that's, I think, an important element because it's how they tie in the modeling that you see in like Markov chains and reinforcement learning with survival analysis. And they say the algorithm can be used as a drop-in replacement to maximum likelihood estimation, and by exploiting temporal consistency, it can dramatically increase statistical precision in certain cases. It's interesting that they say that. So the one of the ideas that they point out is that this is actually pretty simple this is a pretty simple change to what exists already, but it's powerful. And the claim they make later on in the paper is that it's more data efficient. So I'm not exactly sure what they mean by dramatically increased statistical precision, but maybe that means that you can learn, I guess you can learn the important statistics with fewer samples. Maybe that's what statistical precision is in this case. Anyway, so there's two baselines that they talk about and they mention here. No, sorry, is there two or three? There's two. Okay. So the first baseline is actually one they compare their method to against in this paper, which is called landmarking. And so traditional survival analysis is, like I said, oh, there is one more thing I wanted to point out. Is it over here? Or did I skip it already? Okay, sorry. I did skip one important detail of survival analysis, which is, it's described over here. It says the event may not always occur within the observed time window, leading to censored data, which contains useful information but need to be treated differently from fairly observed data. So there's an element here that of this data that is actually something that probably exists in a lot of data that we don't actually take into account, which is, so say that you monitor patients for a period of 10 years and you have 100 patients. Maybe, unfortunately, 10 of them pass away during that time, but the other 90 stay alive. That doesn't mean that after 10 years, they'll never die. It just means that you've stopped recording data. And so that means that you don't have an actual number for when those other patients survive till, but you know that it's more than 10 years. So that's useful, but it also doesn't tell you everything. So there's this element of the data called censored data, which is that you don't actually have the label for all of your people about like how long they survived. And I actually, that's a key element that I should have mentioned before. Sorry about that. So there's for the traditional approach to survival analysis. I'll actually go to the variables all the way. Where is it? Okay. So the traditional approach to survival analysis looks something like this. You have these triplets, and I'll tell you what each of these variables mean. So X is the state. So X would be the description of the person. T is the amount of time that the person survived. And C is an indication of whether the death of the person or the loss of the person was observed or not. So T might be unlabeled and C would be labeled. And that's what a traditional survival analysis looks like. You just have a set of numbers. Like say you have 300 patients, you have 300 of these triplets. But one of the elements of this problem that you all of a sudden have is that you actually have multiple readings of the same person. And that's what landmarking is, which is your data set, instead of looking like these triplets for each person you have a sequence of states, which is XL. You have a sequence of how long they survive from each of those states. So for example, if they survive for 10 years, then, and you record them every year, then after the first year, they actually survived 9 years from the current state. After the second year, 8, and so on. So you have additional labels, and then C is just an indication of whether the person actually ever passed away or left the business. So all of a sudden, you have more data for each candidate, for each person. And so in the related work, they discuss, sorry, let's go all the way back up here. In the related work, they discuss that method of taking advantage of this data, which is called landmarking. And it's exactly the same as the traditional survival analysis. And the traditional survival analysis is you choose some parameterized model and you use a maximum likelihood estimation objective to learn the parameters of that model. In this case, you're using a maximum likelihood objective, again, estimation example objective, but in this case, you have more data because you kind of augment it with the additional sequence states. And then there's another line of research which, instead of doing this, instead of doing landmarking, what it does is it jointly models the sequence dynamics and the survival distribution. So again, this is like dynamic survival analysis, which means that the candidate is, the person is viewed to change over time. And so if you can predict those changes, that can also, that's an important element of being able to predict their survival, because the changes have an impact on their survival, or at least that's what's assumed. So by jointly modeling the sequence dynamics of each of the people and trying to figure out what they are in the survival distribution, you can most likely get a better distribution. And they even say here that in the work that they're citing, that the authors view survival analysis by means of a stochastic process reaching a boundary and explicitly consider the implications of the Markov property. And so actually what they're saying is that this work is really very closely related to theirs. but it doesn't take into account temporal consistency, which is a major element of their model and what they're trying to learn. And we'll go over temporal consistency later. Okay, yeah. But basically, there's a previous work that does almost exactly the same thing without this temporal consistency, which it would have been interesting if they had actually used that as a baseline. Now that I'm thinking about it, I'm kind of surprised they didn't. But I still think the work is actually well written and a good paper, I have to say. They say over here that the dynamic survival problem we consider in this paper is analogous to the so-called policy evaluation problem in reinforcement learning. Yeah, and I actually felt like if you look at the formulation of this paper, it was a reinforcement learning problem written in the notation of a survival analysis problem. Like from that perspective, I don't know how new any of the math or anything is. It's just that they use different variables. But it is, I think that's the whole point, that you can directly apply the ideas of reinforcement learning to this problem. Okay, so let's talk about the preliminaries or their problem formulation. So they consider a sequence drawn from a Markov chain on a state space mathcal X with an initial distribution pi naught of X. So that's just a distribution over how likely you are to start in any state. And this is really important to know if you want any of the math for reinforcement learning to work out. You need to know it. And then you have transition probabilities, which is like, so say, maybe a good example could be if a patient is healthy 1 year, what's the probability they're going to be unhealthy the next year? That could be a transition from one state to another, and it's the probability of that happening.
These are themselves time independent?
Yeah, they're time independent based on the notation they're using.
That, I think, in practice is actually quite a huge impact, right? If you think of survival analysis for customers, say delinquency rates, right? If it can very well happen that as say the economy goes bad, transition rates from an active to an inactive customer change, and that if you fail to model that could lead to a very almost, I want to say, useless model for future predictions if you don't take these things into account.
That's very fair. Two things I would say is that you could augment the state by indicating like the time as part of the state. And here, based on my understanding of the math, they actually don't assume that you have the same probability, the transitions between states, but that's not what this notation indicates. So, okay. Yeah. And so they also say, so X is the state that a candidate is in or a person is in. And then they have their terminal state, which is like empty set, the empty set variable. And they said, we are interested in estimating the time big T until the sequence reaches a terminal state from any initial state. And then they say, this is commonly referred to as the hitting time of the terminal state. Good to know in case you're going to read any other papers on survival analysis. Oh, it's we use the terminology of survival analysis and refer to T as the time to event. So who's if in survival analysis they call it time to event, and then they're saying it's commonly referred to the hitting state of the terminal state. And what other, if I thought this was a survival, I'm confused why they're giving both terms if the one in survival analysis is time to event. Anyway, there are three in survival analysis. There are three very important functions. One is the probability mass function here, which is if you are in a state X, what is the probability that the time to the event will be K? And then you have your survival function, which is if you are in a state X, what is the probability that you will, your survival will be K or more? So if you've just had a treatment, what's the probability that you're going to survive for 10 or more years, for example, as opposed to just 10? And then you have your hazard function, which is, so you've just gotten a treatment, that could be your state X. and you're saying what's the given that I'm going to live for 10 or more years, what's the probability? That's what they're saying here. What's the probability that I will only survive for 10 years? So that's what the hazard function is. So it's kind of like, what's the probability that you'll survive for the least amount of time that's possible based on your survival function. And then they point out that it's possible to express any one of these functions in terms of the other. So for example, the survival function is just a product of 1 minus the hazard functions. And they have a couple of, they point out some stuff here, which I'm not going to go through. It's just, I'm sure it's this way to make the math work out, like how they, for example, they're defining that if you're in the terminal state, that the probability of surviving and is 0. Makes sense. But they're also saying that, actually, no, this all makes sense. It's just, I don't actually know why they're saying it.
Well, one thing that might be slightly off-putting is that K is quantized, right? So somehow people made a choice to bin K, which is not necessarily natural, right? If you think of most natural survival problems, I don't know, nuclear decay or something, it's KK is technically continuous.
Yeah. So Arvid just brought up a good point, which I don't think they've mentioned yet, but they've mentioned, no, they do mention somewhere. They mentioned in the abstract. So as Arvid pointed out, usually survival analysis is predicting the time to an event. Time is a continuous quantity, but they discretize it here. And so that's why there's in all of their functions, K is an integer. It's some kind of positive and a non-negative integer. And then they are also, as part of their formulation, saying that there's a finite horizon of K steps. So for example, you could be training your function to say how many years a person will live and say that the most they could live is 100 years. That's the K. So that's an important part of the math that they're using, actually. And so the other notation that they use here is that they indicate how they're saying that whether a sequence is right-censored, as they called it, which is when you don't observe the death of the person, you just observe that they've lived for a certain amount of time. So they've lived for K, big K steps. And that variable is C. And so this notation here, it's an indicator function saying that the state at x times xt, which is the time that is not the terminal state. Okay, let's see. Okay, so then they go into describing survival regression. And so you might be in some state X, but you can only observe certain features of that state X, and that's what phi of X is, your feature vector describing the person. So, what's a good example of something we can't observe? I don't know. Like maybe you know, there's a lot of things about a person's health that you can't easily observe, or you can't observe you can't easily observe. Like if you're doing home monitoring, it's pretty hard to observe someone's cholesterol if you're monitoring for heart disease. So you might be able to measure their pulse on a daily basis, but you're not going to be able to measure their cholesterol. So phi would only show you their pulse on a daily basis when you actually are more interested in knowing their cholesterol to measure their risk of heart disease. So phi of X is the description of the person that you have available at each time. And that's the input to the models that they're talking about. And they point out their, like they say, intuitively, if two states X and X naught share similar state representations, then the two states should have similar survival distributions. Makes sense. That's just I think that's kind of like explaining a smoothness constraint, that you want there to be a smooth transition between similar states as opposed to like very rapid changes. And they describe like a very popular model I've found in based on talking to the person in charge of our insurance, Dirk, that it's called the discrete time Cox model, and they have it here, or just the Cox model is used a lot in survival analysis, and it's actually really simple. I was kind of surprised. It's a linear model with a bias term, and the output of the model is a single number. It's a scalar. And it's the log odds. So the odds of surviving versus not surviving, or this is a hazard. Yeah, the logs of dying at time step k versus surviving at time step k.
It's kind of interesting, right? Because the alpha or the value has also the time as a as an index, right? So it sort of would take the history into account. You get someone starting versus someone already being in the system for X years. They would get different survival curves based on this same features, I think.
Yeah, that's true.
That makes it actually quite a powerful model, because it's so it has this variance. Of course, getting to these alphas is, I think, the hard part.
Yeah, that's true. And getting yeah. And another, I was actually thinking that, you could make it both state and time, which is actually what they do. You could make the model both state and time dependent. Like, for example, here, or in the math later on, they train a separate hazard function for each time step. So in actuality, Vita, which is a vector, is time dependent too. Anyway. And then, okay, so for survival analysis, they've introduced this model, and then they introduced their training objective. Is so you have n sequences of a person, or of our data points. So you have like n sequences where the state vector changes over time, the feature representation may change over time, it may not. And then you have a horizon of k, which is like probably your maximum sequence length. And you're comparing the survival at time k of each candidate against the hazard function, like the probability that that person will survive at that time. And then it's weighted by, where's the weight? Weight is just like whether it's whether the person survives past that point or not. So that's just a way of turning off sequences once the person has passed away. So yeah, that's the training objective, like the classic one. One thing I was a bit confused about is this notation here, like x and 0, because 0 to me indicates like you're only looking at the first point in the sequence, because n is just showing you the n different patients you have or candidates you have. So I was a little bit confused about like why they don't. Why is the k even here? Like, does the yeah, shouldn't they just be using the how do I put this? No, actually, no, I guess it does make sense. I just was surprised that they're not using the other sequence states in the sequence. But this is traditional survival regression, like traditional survival analysis. Okay. And then you have their methodology, which, what did I? Okay. So their methodology, and they introduce it here with this explanation, is that intuitively, actually, we'll look at these equations, but they say, in this section, we develop efficient algorithms that estimate the survival distribution for any state. Our approach takes advantage of the following key ideas. By the law of total probability and the Markov property, we can write function characterizing the survival distribution as recursions for all k greater than 1 and x like state in the state space. And so that's saying that the probability of surviving to point k, or being, I guess it's, no, that's the probability of dying, which is the probability math, given your state is equal to the expected value of like your current state given all the states you are in you could go and transition to in the next step, and you decrement the time step as well. I'm not explaining it super well, but I would encourage you to just like take a second to look at these equations because they describe the temporal consistency idea that they're talking about, which is key. You can see that they've gone from state k to from time step k to k-1 if you go from the left to the right, and they're just taking the expectation over future states. And the interesting thing about this is they're not making this as an assumption, they're making the Markov property as an assumption, which is often a very loose assumption you can make about things. Yeah, and to make the math work, they later on say, let's assume the state space is finite and has cardinality x, like that's the number of states in it. Okay, so there's a lot of math, but I guess I wanted to talk about value iteration in reinforcement learning because this is basically value iteration and reinforcement learning from like maybe a process point of view. So the way that really traditional reinforcement learning works when you have like a finite state space and a finite if it's a finite state space is that you usually if it's small enough, and let's assume it is, you actually learn a table, a lookup table, which tells you like the value of each state. And the way that it works is that you randomly initialize that table usually, and then you perform value iteration on it. And each time each iteration that you perform it, the table gets more accurate in terms of estimating the value of each state. And then at the end of it stops when you stop value iteration when you converge in terms of the table values. And so that's exactly what they're describing something very similar here. And the point that they're trying to make with these first three steps, or these three equations that I'm going over with my cursor, is that so you can represent a survival function as a matrix, which they're calling Q. And Q star is like the correct or the survival matrix for the problem. And one point that they make is that if you take the survival matrix for the previous step, so for example, from up to step k-1, you multiply it by the transition probability matrix, which is P, then you'll get the survival matrix. So what this indicates is that you can start with a maybe not an incorrect, but you could start with like just the first step of your survival matrix and calculate it just using the transition probabilities. And yeah, I'm not going to go into all the math because I didn't really prepare that much to talk about it. But the gist of what they're saying here is just that you can estimate the survival function in an iterative approach where you initialize your survival function or your Q matrix with random values that I think they have to be linearly independent by row. And then you can just iterate through them with this transition matrix to get the next transition matrix, and you'll converge to the correct one. So this one is talking about, like this section 3.1 is talking about in the exact case where you are not approximating the survival function. And then in section 3.2, they're talking about the approximate case. And as long as your approximate model has meets some assumptions, then you will also be able to converge to the correct, not the correct, but like the maximum likelihood estimation survival matrix based on your data. Yeah, if anyone has any questions about this, I'm happy to try to answer them, but I was just glossing through it because it's just a lot of theory that then leads to this very simple algorithm here. This algorithm, actually, I spent a lot of time looking at it because I was like, there's parts of this that I don't I understand it, but I was like, oh, this is a bit surprising to me. But so the short version of what is said here is that you can take an iterative approach just like you would with value iteration to learn a survival function. And that's what they're doing over here in algorithm 1, temporally consistent survival regression, which is they take all their sequences and separate them into sequence pairs. So say you had n sequences of size 10, then you would have n times 9 pairs in your, and that's what m would be, big M is. And so for each of the sequences, you have this pair, which tells you, for example, whether in the next state you transition to the terminal state. That's what line 3 is. 4 is just waiting the point for when you're training. And then what you do is you propagate through you basically generate a trajectory, and you make sure that the hazard function and the survival function are consistent, and they meet the temporal consistency objective that we were talking about before. And that's how they enforce temporal consistency as part of their training. So the first step is like actual labels, which they call hard labels, of whether the candidate survived or not. But the rest are just making sure that if the candidate didn't survive, that the function is actually meeting the temporal consistency objective. And you can see how this is trying to meet temporal consistency if you like pass these variables into the equation. So y and k in this case is just the hazard function for one step in the past, and it's saying that you want the cross entropy or the probability outputted by the hazard function one step in the past to be close to the hazard function one step in the future, weighted by the survival of 2 steps in the past. I haven't really understood why the survival function is used to weight each of the points in your training set. But anyway, the key idea here is that you perform all of these calculations in the 2 for loops, and then you calculate this training objective, and you update your parameters of theta, for theta, which is your survival function parameters. And there's no guarantee that within the first iteration that you'll get the optimal parameters, which means that you'll have converged. So that you continually do this until theta converges. And then if you look back in the math, they show that for some models, you have guarantees of convergence and within a certain number of steps. So like within k steps, I think. But anyway, that's the whole idea, that you continuous that every iteration of these 2 for loops and then this update, the theta parameters will get better until they converge to the maximum likelihood estimation values for that for the parameterization of the survival function that you've chosen. Let's see. Okay, yeah. And proposition 3, algorithm 1 is equivalent to the fixed point iteration with the empirical Markov chain and state distribution. That is basically saying that this is equivalent to value iteration in reinforcement learning. I'm going to go through that. Oh, yeah, I'm not going to go through there. Okay. They say that you can apply this entire method to continuous state spaces as well. And you just have to make sure that you use smooth parametric functions for the continuous state space. And then they just talk about the connections with RL, which we've talked about quite a bit. And then they talk about experimental evaluation. So the paper's main claim to fame that they have is that they are more data efficient than previous methods. Like they all get about the same performance. I was actually really interested to look at the data sets they use, because it actually becomes pretty obvious that maybe one of the reasons why this is novel in 2022 is just because we don't have a lot of data that we can use to test survival analysis. Makes sense though, because usually it's about patient outcomes, which take a long time to estimate. But anyway, so they have two baselines. They use the same parameterized survival model for all of their functions, which is just this Cox pH model. They do say that you could use a neural network if you wanted, and I was wondering why they didn't. But I also like when a paper uses a really simple model and shows good results. So they compare their training method to one, the initial state method, which is just traditional survival analysis when you don't have multiple readings of the same patient, and then landmarking when you do have multiple readings of the same patient, and you just treat each one as if it's a separate instance of training. Yeah, they've released a paper. I mean, sorry, they released a repository with the code if you want to try to replicate it. One nice thing about these methods, I think, is that you can completely replicate the results, or you should be able to, because there's actually there's stochasticity in the transition functions. But if they give you the data that they generated, it should be. The training process itself is actually, even the training process is stochastic. So you shouldn't easily be able to replicate the results exactly, but probably get similar results. Sorry, just thinking out loud here. Okay, the statistical benefits of temporal consistency. Wait, where do they talk about the data sets that they used? Oh. Because I wanted to make sure that I said what they were. I can't click on here. Okay, it's over here. So we'll get to that after, because I guess their first experiment is on a synthetic data set. So their first experiment is with a concrete data set where they're kind of here's their what is this called again? Here's their graphical model for their state space. And basically, this is the sequence 1 through L for the synthetic problem they've created. And A is supposed to be you're a healthy patient, and B is you're not healthy patient. And these are the probabilities of terminating based on which state you're in. And then these are the probabilities of staying in the current state you're in. And at each time, there's a chance that you're in one of these two states. So what they show over here is that the landmark. Oh, and what they're trying to model is the effect of different treatments for some disease, or maybe just a healthy person trying out different things to live longer. And I guess there's some shared structure between the impact of these different treatments, because the main thing they show is that if you look at this chart here, the Kendall tau metric that they're using is a measure of how good is the ranking of treatments based on the models. So you have these survival analysis models for these different treatments, based on the survival analysis, which one is the best. And the temporal consistent survival regression, which is their model, it is able to improve its performance as you get more and more treatments. Even though you have a small amount of data for each treatment, you only have 10 sequences. And so they say that what they're saying is it says, by leveraging the Markov assumption and regression predictions at A and B on the initial states, we remove a large part of the statistical noise in the individual sequences. So I guess the statistical noise is just they only have 10. How many do they have? They only have 10 sequences per treatment, and the treatment affects survival, but I think I guess it affects survival by affecting like what's your likelihood of going to healthy or unhealthy. A is healthy, B is unhealthy. But the other state transitions that they show here are fixed. So I guess the model is able to learn those and consequently rank the treatments more effectively than the landmarking approach, which isn't able to like take advantage of the shared structure between the different treatments. And they say, oh, that's because landmarking is fundamentally unable to make use of the data pooling advantage. So here they're just showing that one of the like the benefits of using this TCSR instead of landmarking. And then they compare it against 3 different data sets. They use 2 different metrics. One metric is the concordance index, which is again like a way of measuring how good the ranking of the treatments are. And then the other one is we evaluate a model by measuring the root mean squared error between the regression coefficients beta and the gold standard coefficients beta star. One interesting thing I found was they calculated the gold standard coefficients beta star by just doing maximum likelihood estimation on the full data set. And I was wondering if that's correct. Because if that's correct, then why don't you just a priori calculate those and put them into your model, and then all you're estimating is the alpha terms. Anyway, they had 3 data sets that they evaluated on. One is it was 312 patients diagnosed with PBC, a rare liver disease. Patients' features include static information such as gender and treatment, and 12 dynamic biomarkers that are measured at study entry and at the follow-up visits. The second study follows 416 patients diagnosed with HIV and AIDS. In this study, a single dynamic biomarker of the CD4 cell count is measured repeatedly. Where's the third one? The studies span multiple years, blah, blah, blah. And then, and we complement these clinical data sets with a synthetic data set based on 20-dimensional random walk model. And so they have another synthetic data set they create. So one thing I was like, wow, there's only 312 data points essentially in one and 416 in another. So this is definitely a model that's being applied in the small data regime. Another reason why probably a simple model is better. But what you're supposed to take away from these charts, which are telling you about the performance of like their method in red versus landmarking versus the initial state, is that their method requires many fewer sequences in order to get as good performance as the other 2 methods. So in the first case of the PBC 2 method, they quickly, I think with the fewest number of sequences, they're able to get the rankings right and get the right linear coefficients. With the AIDS one, they aren't as able to get as good difference in performance, but they point out that probably the dynamic element of the method, like the CD4 measurements, are not that indicative of health or of survival. So it's probably not a useful information. So that's why their method probably doesn't perform that much better. And then in the random walk, they perform better, but it's a synthetic. It's like a completely generated data set. So yeah, the main thing they say is they have better data efficiency. Another interesting thing about this method in respect to a lot of the methods we use is that they don't actually use gradient descent. Or do they? No, they use Newton's method. They don't use like stochastic gradient descent. And they use SciPy. And it's not that, they're saying it's not that long to train these methods. Cool. And in their conclusions, they say there's 2 different ways that they would like to extend their analysis. One is that all their analysis was with the idea that you're trying to predict a binary feature, which is survival, like whether you would survive or not. But what if you want to, what if there are multiple events that you're trying to predict for instead of just survival? So that's what this competing risk setting is, where instead of having a binary problem, there's multiple risks that you're trying to predict for at the same time, when they'll occur. or they want to do their extension to irregularly sampled continuous time sequences, which actually is like one of the major things that they do in their experiments is that in all these cases where you have multiple readings, I think in the PBC case, the readings are at uniform intervals. But in the case of the AIDS patients, they're not uniform and they're not at the same time as each other. So they actually just say like, let's assume that they happen at uniform intervals in the way that they've modeled it. And that, so yeah, they haven't really figured out how to deal with when you're making measurements at irregularly timed intervals. So yeah, that's the paper. Cool paper, I thought, because I was like, oh, I've never really heard about survival analysis before. Well, I've heard about it, but I've never read about it. And a lot of interesting kind of math and combinations of things. So I liked it.
Yeah, thank you very much. Very interesting paper.
Nice. Okay. Well, does anyone have any questions, or we can just finish early?
I'm good.
Okay. Yeah, well, thanks. Let me stop sharing. Thanks everyone for coming. And hopefully, I guess everyone, Innika, hopefully you'll come too. Innika and Arvid, I hope I see you both at Data Spartan next week. We're having an in-person paper club. Cool.
I think I never met you in person, actually.
He's talking to you, Innika.
Sorry?
Arvid's saying he's never met you in person.
I think so. Because I